So last time we introduced solvable nilpotently algebras, and in a way it's a way to define algebras that are close to a billion. Right, so they are not a billion, but after doing some operation, finite number of times, you will get an abelian, right? So in today's seminar, we'll introduce something that is kind of opposite to abelian, which is semisimple Lie algebra. So the first definition. Well, first simple Lie algebra, so Lie algebra G is called simple if it is not abelian, first of all, and it has no proper non-zero ideals. That's the definition of simple, and then let me define semi-simple. The Lie algebra G is called semi-simple if it has no non-zero solvable ideals. If it has no non-zero solvable ideals. Yeah, so what is a natural question to ask here?
Sorry, can you remind me what is a proper idea?
Proper means it is not the whole Lie algebra. Sometimes non-zero also is included into the definition of proper, but I just wrote it down explicitly here. Right, so you have some property and semi of this property. So the question is if actually simple or semi-simple, right? It's so of course it is the case. So it's our first easy proposition. G is simple. Implies G is semi-simple. Okay, so let's prove it. Prove by contradiction. So I have to assume that I have to assume that G has some non-zero solvable ideal. Okay, so E inside G, it's non-zero solvable ideal. Then well, it cannot be proper, right? Because G is simple. So therefore, the only way for such an ideal to exist should be the whole G, right? So G is simple. Therefore, G I is coincides with G, and therefore G is solvable, right? In particular, it means that if I take a commutant, it should not equal to G, right? Otherwise, so commutant, let me remind you, is a first element in derived series, right? And therefore, if it coincides with G, then I again take D, and well, then derived series will never go to zero, right? Will never stabilize to zero. It stabilizes at the first step at G, right? So therefore, we have this. But on the other hand, G, it's not zero, right? Why? So if a commutant is zero, it's abelian. But we agreed that simple is not abelian. So therefore, this is a proper non-zero ideal. And this is a contradiction, right? All right. Actually, I would like to think about semi-simple always as a direct sum of simples. It's not clear from the definition that I gave you right away, but we'll prove it. For that, we will need more instruments like invariant form, like non-degenerate invariant form. But so we'll have this result that semi-simple, G is semi-simple if and only if it is a direct sum of simples. Then this proposition is kind of obvious. But for theoretical reasons, to get some general statements, it's better to introduce it like that. Okay. So what would be an example? It's our favorite, I don't know, maybe one of my favorites. Lie algebras, it's SL2. Well, say over C. This we can see right away that it is actually simple. Not even semi-simple, but simple. So let's see. You have SL2 has a basis. So it's a span of E, F, and H, right? And the relation is E, F is H, H, E is 2E, and HF is negative 2F, right? So suppose I have I non-zero ideal in SL2. And let us check first that if it contains either of E, F, or H, it coincides with the whole SL2. Right? So suppose, so case 1, assume I contains H. Right. Then, because of this, it contains E and F. Right? I is an ideal, right? Therefore, if I take H, which is inside I, and commute with anything which might be outside of ideal, I'll get something in ideal, by definition of ideal. So therefore, E and F, so let me call this this 1, this is 2, and this is 3. So by 2 and 3, E and F belongs to I. So 2, assume that, well, E, for example, is inside I. E inside I. Then I would like to argue that H is inside I, right? This is by relation 1. And therefore, by the case 1, I coincides with SL2. Right? E, F, and H, they are all inside I, and therefore I coincides with SL2. So then, by case 1, I coincides with SL2. And case 3, well, case 3 is just similar to 2, right? If F is in I, then we just do similar computations.
Sorry, the last statement that was proven is that SL2C is what kind of algebra?
We're proving that SL2C is simple.
Okay,
So, but we didn't finish yet, right? For now, we so suppose one of these standard bases, one of these elements inside I, then I is coincides with SL2. That's the statement. Well, 3 F is inside I, then similarly 2 I coincides with SL2. But then I would like to apply lemma, the following lemma. So suppose I have so lemma, and we can discuss. Let me formulate it. Discuss why it's true. It's pure linear algebra. So suppose A is the diagonalizable matrix with different eigenvalues. Well, and A is it actually Right, and suppose I have, so A is, say, n by n matrix, right? So it's from this, say, right? Then suppose I, right, is a subspace of Cn such that invariant with respect to action of A. That's what I would like to say. So I is inside I. Then I is a span is spanned by eigenvectors of A. So where V1, Vk eigenvectors of A. Some, maybe not all of them. Okay. So first, maybe just to motivate to think why this is true. This is a pretty easy statement from linear algebra, right? We would like to apply this lemma to H. So H acts on SL2, right? So in this basis, E, F, and H is diagonalizable with different eigenvalues. So take, in this lemma, take A to be, I should say, at H. Well, it's not a matrix, it's a linear transformation. It lives inside here, right? SL2. But, so I should say in basis here E, F, and H. Then what is this matrix in this basis? You tell me.
0, 2, -2.
Yeah. Well, maybe in this order, since I wrote it. 2 minus 2, 0, right? Well, E is an eigenvector of at H with eigenvalue 2. Then F is an eigenvalue of at H with eigenvalue -2. And then, well, H commutes with itself, so it's 0 here. So it's diagonalizable with different eigenvalues, and therefore, if I have some ideal in SL2, it's also invariant with respect to at H, right? So therefore, it should be a span of elements which I choose out of E, F, and H. But we proved that if at least one of them belongs to I, then I is everything, right? So SL2 is simple then. Now, why this lemma is true? Well, because you can consider, so this is a linear transformation of Cn. You can consider its restriction to I, right? And consider all eigenvalues, and like consider its Jordan normal form of the restriction, right? And all eigenvalues and generalized eigenvalues will be, of course, its eigenvalues and generalized eigenvalues of not restricted A, right? So therefore, if it's diagonalizable if A is diagonalizable, then restriction should be diagonalizable too, right? And all eigenvectors that I take for restriction are eigenvectors for non-restricted metrics. So that's why this lemma is true. Yes. So any questions?
The beginning and the ending of the lemma is
Yes. No. So lemma, this is the formulation. Beginning here, end is here. And since it's just pure linear algebra, I just motivated in words why this is true. But SLN is also simple, actually. Right? We last semester we studied SLN a lot, and so this semester is kind of generalization of what was discussed last semester. So we will develop all this machinery of weights, highest weights, not only for SLN but for all simple algebras. In particular, SLN is simple, but to see that it's a good exercise, and maybe for next seminar I will give it. It can be done. It can be done in a similar way, but it can be done in more fun way, like just using representation theory of SLN that you already know. Also. Anyways, let's continue. So next proposition. So now, if I have an algebra, I would like to kind of separate two parts: solvable and everything else. Right? Everything else happens to be semi-simple. So that's our goal to see that. So proposition. Any Lie algebra has a unique maximal solvable ideal. Let's prove this. Well, again, I should say, but by default, our discussion is about finite dimensional algebras, right? So let us agree again that for now, like we're talking about finite dimensional algebras, and let me not write it all the time on the board. But this is crucial here. So let what would be the candidate for such maximal solvable ideal? So let I be a solvable ideal in G. So let's call our Lie algebra G. Let I be a solvable ideal of G of maximal possible maximal dimension. So maximal it means that it is not contained in some other proper ideal. So if it is contained on, so if you found something that contains this ideal, then it is G itself. It's not something, there's no something between G and this ideal with respect to inclusion. Yes. Okay. Thank you. So, yeah. So let us take I, solvable ideal of maximal dimension, of maximal possible dimension. So I would like to prove that it is actually maximal with respect to inclusion.
It's true that it contains all other solvable ideas, or can there be solvable ideas that are not maximal but are not contained in the maximal?
It is true that it contains all solvable ideals.
Okay,
Yeah. And actually, that's what we would like to. That's our next statement. So let I prime be some other solvable ideal. Then I would like to see that it is inside I. Okay. For that, let me consider I plus I prime. So I would like to see that this one is solvable too. But it contains I, so therefore it should coincide with I. Right? So that's the trick. So let me take I plus I prime and quotient it by, I don't know, I by I. Okay. Question?
Why don't we just obtain I prime?
Sorry, say it again.
Why the result of this operation is not just I prime if we factorize with respect to
No, it is not a direct sum. They can intersect. So that's the point. So it is actually I prime, right, by intersection by this. So if they don't intersect, then the result is I prime. And this is called, I don't know, like a second isomorphism theorem or something, right? In your abstract algebra class. Anyways, so I prime is solvable. This is quotient of solvable ideal, which is also solvable, right? So this is, so therefore, I plus I prime, quotient by I, is solvable. It's a quotient of, so as a quotient of solvable ideal. I think last time we proved that the quotient of solvable is solvable. And on the other hand, I is also solvable, right? But we had the statement that if quotient is solvable and what we quotient by is solvable, then the whole thing is solvable too, right? So therefore, I plus I prime is solvable. But it should be, but it contains I, right? And but I is of the maximal possible dimension, right? So therefore, dimension of this thing is not bigger than dimension of I. So this should coincide with I. So therefore,
Sorry, again?
yes. You have this, right? I is inside I plus I prime. Right? This one is solvable, and this one is solvable. But this, among all solvables, have maximal possible dimension. So therefore, dimension of this cannot be bigger than the dimension of this. So therefore, they coincide. So let me maybe write this down. So dimension of I plus I prime is less or equal than dimension of I. So this means that I plus I primes. So therefore, I equals I plus I prime. Right, and but this guy includes I prime right. So therefore, I prime sits inside this one, which is I. So we proved this. So we found an ideal that actually contains all other proper solvable ideals. Right? And of course, it's unique, right? Because suppose that we have another one that contains all others, but we have then both two-way inclusion, right? So therefore, I is unique, proper, solvable. Shouldn't say proper then, right? Solvable. So unique, maximal. It can coincide with G itself, right? Maximal, solvable, ideal. So this ideal has name, which is called a radical of G. So definition, I from the proposition is called radical of G, and we denote it like this, rad G. Okay, so now a theorem. Okay, we kind of found the solvable part of our Lie algebra, right, which is the radical. Now, what's left? Well, we should take quotient and see what happens then. So the statement is that the quotient is semisimple.
Does this coincide with the notion in algebra geometry when you take the radical of an ideal?
Yeah. So it means that radical of an ideal. It means that some power of an element lives in this ideal. I don't see immediate relation. So
maybe from that definition we obtain this property here about the maximal solvable.
Here the maximal solvable ideal means the maximal element in the set of all solvable ideals.
yes.
It's maybe not a maximal ideal.
It may be not maximal ideal. Yes, it can be contained, yes, in some other, but this ideal then is not maximal. is not solvable.
I'm sorry.
Yes.
Are all ideals embedded one in another? Or
No, that's not true. It's they can intersect. No. I mean, they can intersect. So you can have situation like this, right? So theorem so if you take any G quotient, so it's radical is an ideal first of all, right? So we can quotient by it. Take a quotient. Then you get semisimple is semisimple. Okay, so another statement which is converse of this, right? So this is statement number 1, and 2, if G quotient by B is semi-simple for some ideal, I should say solvable, I guess, right? Let me B, then B coincides with radical. So this is semi-simple. So proof. Let's first proof the part 1. So again, how we usually prove that semi-simple? We suppose that I inside G by radical G is solvable. Then we should prove that it is actually 0, right? So how do I do this? I take, so I have a canonical projection, right, from G to G radical G. And let me take pi inverse of I tilde. All right. So if I take this one, then I, right, is then I tilde by radical G, right? So I is solvable, radical G is solvable, therefore I tilde is solvable, right? A and radical are solvable. Therefore, I tilde is solvable. Also, it's an ideal, right? It's not only subalgebra, but it's an ideal. And therefore, I tilde is actually coincides with radical. Right, I tilde contains radical, but because it's solvable, it also contained in radical. Right, so two-way inclusion, therefore we have this. Right, therefore I is actually 0.
Should we prove that I tilde is a subalgebra?
Well, let's see. It should be actually an ideal, right? So let's see that. Let's check again. So I tilde. So ideal. So I take something, some x inside, y in G, right? Take the commutator, should be an I tilde, right? So let me take pi of this. Right, pi of both sides to projection. So pi of this equals to pi of this. So I have pi of x, pi of y equals to pi of z, because pi is homomorphism of Lie algebras, but pi of x is inside I is an ideal. So therefore this lives inside I, so therefore z lives in pi inverse of I. Okay? Works. So therefore z is in pi inverse. Very well. So the second statement, so proof of 2. Should be even easier. So this is semisimple for some solvable ideal B. So it's solvable, therefore it is inside radical of G, right? On the other hand, right. So I take radical and quotient by B, right? B is an ideal in G, but also it's an ideal in radical, right? This is then an ideal in G quotient by B. But this ideal is also solvable, because radical is solvable. But this one is semisimple. So therefore, this one is 0. So this is semisimple. So therefore, radical of G over B equals to 0. So therefore we have the statement radical coincides with B. Very well. So the next statement is the following. Theorem says that radical in every irreducible representation, radical acts by multiplication by scalar. They act as scalar matrices. Okay, so so let V be an irreducible representation of G. Then radical of G acts on V by scalar matrices. So what it means that if I take an element in here, right? Since V is a representation, it can be sent to endomorphisms of this representation, right? And this is endomorphism is just multiplication of every element of V by the same number. Numbers might be different for different elements of G, but so this is what it means. Just in every basis, actually, it is just, well, there are some bases in which every element in here is just C times identity. So that's it. Moreover, there's another part in here. If you consider some ideal inside here, which is radical G, commutant of radical and G. So this thing acts by zero. Okay, let's try to prove it. Right. So remember this lemma that we discussed when we discussed Lie theorem. That if I have a solvable Lie algebra, right, then in every representation I can find a common eigenvector for all elements in this solvable Lie algebra. Right? So this was the crucial step from which Lie theorem followed. So now let us take this. So we have a solvable Lie algebra which is radical, right? And let us take this common eigenvector V. So let V be a common eigenvector for radical of G. So it means in formulas, it just means that there exists some map, right? So there exists some map. This is actually linear. Let's call this map lambda. It is from radical to just complex numbers. Such that if I take h, right, so for every h from radical G, if I take h, act on V, then it gives me this, the value of lambda at h. It's just a way to, write this down.
Character or is or
Yeah, if it was a group, it would be a character, right?
I mean, does this map have to respect the operation on the operation in radical G?
It does, yes. Just because of property of eigenvalues, right? Right. So you have this. Next, let me take V lambda inside my V. V subspace defined as follows. Defined as follows. I take, so V lambda is OV and V. V is bad because we already fixed all W's, right, in V, such that HW equals lambda of HW for every H in radical G. So our goal, so see, this is V lambda, right? These are all vectors, all eigenvectors, common eigenvectors for radical with eigenvalue lambda. So our goal is to see that V lambda is invariant with respect to action of G. Then we are done, right? Because V is irreducible, and therefore V lambda should coincide with V, right? Okay, so let's try to see this. So let's just take some W from V lambda, and let W be not 0, right? I would like to check if I act by X from G, it stays in V lambda. For 0, it's evident, right? So let's just take something not 0. Then let me take X from G, just any X. Let me take act by X on W. And then let me take H from radical G. So I would like to see that if I act by H, then it gives me lambda of H times the following. So I can commute, right? So it will be, so I pull H through X, it will be X, H, W, plus commutator of H and X, and W. So H acts on W, we know how, right? Because W is from here, it's written. So let me continue. It is actually lambda of H x W right? So this guy lives in radical as well. Because radical is an ideal, so and H is in radical, right? So therefore, I can write here lambda of Hx W. All right. So now let me take yes. So next step would be to prove that this is 0, right? How do I?
Lambda or the commutator?
Yes, so lambda of this guy is 0, right? Of commutator. Yeah. How to prove this? I would like to use like a trace as an instrument. For that, let me actually form like a sequence of vectors. So let me start with V, which is this V over there, and then apply X. So then X square, right? Well, this is in universal developing, but right, two times X, and so on, right? So actually, let me denote WK to be X to the KV. I would like to take as much W's as I can to make them linearly independent, right? At least V is not 0, right? The second might be already linearly independent, then I stop. But I continue doing this, right? So let n be such that be maximal such that W0, W1, and so on, Wn is linearly independent. No, linearly independent. And let me take span of all this W0 to Wn. So let me denote W to be the span now I use this, and this is a basis for W. And in this basis, right, H acts by upper triangular matrices, and on diagonal, I have this, right? So in any case, so if I have, right, so I take Hx, right? I consider them the image of this in W, like W is invariant with respect to this thing, right? Just because of how we construct this. Right. So I take trace over W of this. So trace is cyclic. So this is 0. But on the other hand, I claim that this is dimension of W, right, times lambda of Hx. Okay. Because on diagonal we have lambda of hx, right? Every time. And something else off diagonal, right? Which is in upper above diagonal. But we need trace only, right? So the trace only involves diagonal elements, and they are all equal, right? So when we sum them up, it will be dimension of W times what stays on diagonal. So this is not 0. Because at least V is inside W, but V is not 0, right? But this is 0, so therefore this thing is 0. And so we're actually done, because so we proved that this thing is 0, right? So it means that hxw is lambda of hxw, right? This is gone. This is the only term that is left. Therefore, V lambda is invariant with respect to the action of G. So therefore, V lambda coincides with V. So that's it. And we actually proved on our way here that like commutant of radical G and G acts by 0, right? So that's our statement. So this is from radical G, this is from G. All right, so for some, so it would be nice for us to kind of distinguish Lie algebras where we don't have elements, non-zero elements, that act by 0 in a reducible representation. Because we kind of lose a lot of information in representation theory then. Okay? So we would like to, distinguish and say that such Lie algebras are nice. So we would like to distinguish Lie algebras such that radical G with G is 0. But this is equivalent to say that the center of G is 0. The center of G coincides with radical, sorry. Right, so maybe let us formulate this as a lemma. Kind of obvious, but radical G with G is 0 is if and only if that center of G coincides with radical of G. Okay, does everybody remember what is the center of Lie algebra? Yeah, so all the elements such that commute with everything else. Yes. Why this is true though? Center is solvable. So it lives inside, right? Radical. But on the other hand, center, by definition, is the maximal ideal of G such that, so by definition of center, this is maximal the maximal ideal such that well, G center of G is 0. Right. In any case, so if I have centers inside radical, right? But this says that everything inside radical commutes with everything in G. So actually, radical is inside center. Maybe even without this confusing words, right? Maybe let me. It just follows. So, but this one, radical of G, comma G equals 0, it just means that everything in radical is inside center. And by the way, both ways, right? So it's actually equivalence. So we have two-way inclusion, and that's it. Very good. So we would like to distinguish such algebras, and there's a special name for them. They're called reductive Lie algebras.
Reductive are those that have this commutator being equal.
Yes, or equivalently, center coincides with radical. So definition. Lie algebra G such that radical coincides with the center.
I'm sorry. If we are always talking about Lie algebras,
Mm-hmm.
Does that mean that multiplication here denotes the adjoint action? Or
No. So this dot x, it's an action. This is if you wish, it's a multiplication in universal enveloping algebra. Do you know what is universal enveloping? Okay. Or you just I'm using notation. So I'm thinking of x already as an element in linear transformations of W, right? So this is a matrix, if you wish. So I first apply one matrix and then another. So maybe it is like that. I should write. But of course, I don't like to write such things every time. So I'm just abusing notation. But this multiplication is ideologically, they are in universal enveloping algebra.
When we, so these the commutators which are used in these commutants are the operations in the Lie algebra, not the commutators that are defined.
Yes, you should be careful. You're right. You should be careful between brackets in abstract Lie algebras and brackets in matrix Lie algebras, which are where brackets are commutators, right? But since representation actually respects brackets, right? So for matrices, the brackets are commutators.
In these commutants, are brackets abstract or are they the commutators? Or is it the same in this context?
So for example, here it's abstract.
Yeah.
Here
I mean in
it is.
in this commutant, radical G, commutant 3.
Here abstract, yes.
Okay.
But we also have Ada's theorem, which says that every finite-dimensional Lie algebra is actually subalgebra inside GLN. So it's not a big sin to think about brackets as commutators. It's a very non-trivial result, though, but it's true. Which is equivalent to say that finite-dimensional finite-dimensional Lie algebra has faithful representation. Say it again?
Since he has not confused why the bracket can be written as a commutator.
Yeah, also universal enveloping algebra, it's an associative algebra, which is Lie algebra automatically then. And again, commutator there is just like break is there is also it's actually commutator, yes.
That's what I was asking about.
Yeah, yeah. But here, like by default, this is some abstract bracket defined on abstract Lie algebra. How much time do we have? 3 minutes?
15.
15, okay. Yeah, so you have this. So let me announce a couple of results then. Yes, a Lie algebra such that this happens is called reductive. Let me finish this. This is one thing. Another thing is that let me announce a couple of theorems. I don't know to which extent we will see the proofs of these theorems, but in any case, we need more instruments to prove that. So theorem 1 actually says that for any reductive Lie algebra G, we have the following decomposition. G decomposes as a direct sum of its center and another ideal, actually, since it's a direct sum of as Lie algebras, GSS, which is semi-simple, where GSS is semi-simple. And there is a more general result, which is called Levi decomposition. I mean, it's yes, it's more general. So theorem 2 which is called, I don't know, Levi theorem or Levi decomposition theorem. Levi's decomposition. If I take any finite dimensional Lie algebra G, so for any finite dimensional Lie algebra G, we have the following. It decomposes, but not as a direct sum, but semi-direct. So actually, we talked about semi-direct sum of Lie algebras, so let me formulate it like this. So I have G. So now I have instead of set center, which coincides with radical for reductive. Here I have radical. So let me still use this sign, but this is not as Lie algebras as vector spaces, right? Okay. So this sign here as vector spaces. But what is important is this. This is Lie subalgebra. So where GSS is a semi-simple Lie subalgebra. So what's important here is that this is a direct sum as Lie algebras. It means that if I take something, it means that this is an ideal, not only subalgebra, but ideal. If I take something from here, compute bracket, this will be 0, right? Here is different. If I take something from here and something from here, compute bracket, it might not be 0, but it falls in this one. But this is a Lie subalgebra, means that if I take two elements in here, compute bracket, then it stays in here. Of course, from theorem 2, we have theorem 1, right? Because if I have a reductive, then radical coincides with center, but then of course, center commutes with everything, right? So therefore, if I take something from center and something from GSS, then it compute commutator, it will be 0.
Do you mean if you change this into semi-direct product, then the left-hand side is isomorphic to right-hand side as the algebra?
Yes. And the action is actually like an adjoint action, right? It's like the most natural way, the most natural derivations. Like to get semi-direct sum, you need one algebra to act on, to be mapped to another, to derivations of another. So in this case, this derivations is taken in bracket. Yeah. But even without that, even without these details, I just can say that this is subalgebra, and this is already means that it is a semi-direct. Right? We proved that. We proved that result that if you have like a sequence, short exact sequence, right, and you have a section, then it is a semi-direct sum. So when I say that this is subalgebra, it means that I have a section, right? In any case, so the in modern words, proof. So this proof of this will follow from complete reducibility of finite dimensional representations of semisimple Lie algebras, which is actually, in modern words, it's a result of homological algebra. And I don't know which way we would like to prove this, so we'll see. Maybe we don't like to prove this at all, I don't know. But this is also, so if you know something about homology, like Lie algebras have their own homology. So this theorem is connected with the vanishing of first homology, this one with vanishing of the second homology. So in any case, so maybe let us talk about some. So let us move on. So the next thing that I would like to introduce is invariant forms on G. So definition. A form, a bilinear form B x y on G is called invariant yes.
What, I repeat basically the same question, but what is the multiplication in this bilinear form?
It's not
I
like
mean, if it contains the terms that are quadratic and in x and y.
Yes, you just this is a multiplication, just a multiplication of numbers that you're talking about, right? This is just multiplication of coordinates. You're thinking of coordinates already.
So we think of it like a bilinear form on the vector space, not on.
Yeah, it's just what is bilinear form? You take two vectors, right, and send them to number. Bilinear means that if I multiply this by number, it just goes outside. And the same here. Well, and the sum goes to sum for both entries. Yes. It's called invariant if we have the following. So x, y, z equals b of x, y, z. So I can take this bracket and then shift it to this, shift it like that, if you wish. So actually, a form, right? Why it's called invariant? Because form is an element of G star tensor G star, right? You have a joint action on G, therefore you have an action here. So this says that B is an element of this representation of G, such that if I act by Y on this element, it is 0. I mean, action of G on this element is just 0. Invariant means is in terms of groups. If you think of groups, right? So infinitesimal transformation is 0 means on a group you stay on the same. Like group doesn't change a vector, but the algebra just kills it. Right? That's the word where the word invariant came from. In any case, as proposition, suppose you have So if you have an ideal I, so let I be an ideal. In G. Then you can consider the orthogonal complement. This is all elements in.
Orthogonal with respect to what inner product?
Yes, with respect to B.
Oh, okay.
So let I be an ideal, be an invariant form, I should say, right? So let B be an invariant form. Right, then orthogonal coupling with respect to B. So let me write this down explicitly. X and G such that B of X, Y is 0 for any Y and G. Sorry, I should take here I, right? So since it's orthogonal complement to I. So be an ideal, then this thing, orthogonal complement, is also an ideal. Well, this is almost obvious. Let's check. So I take X from I orthogonal, Y from G. Right, I would like to see that X, Y is from I orthogonal. So I need to check that the B of X, Y with Z is so the question is it 0 for every Z? Right? Then I checked. Well, I use invariance of the form, and then it will be X, Y, Z. And since Z, right, so Y is from where? From G. Right? I should rather maybe use the other way, right? So let me actually first interchange this, right? So first I interchange, I will have negative B of YX Z. And then I use invariance, so it's negative B Y X Z.
I'm sorry. Is the bilinear form defined to be symmetric, so that you could
No. I don't use.
change the order of Y.
Sorry, I don't use any symmetry or anti-symmetry. I interchanged two elements in commutator.
Okay.
Then I get minus inside, which I can go outside because of linearity of the form.
Okay.
And then the X is from I, orthogonal. So therefore, right. Z should be, Z should be from where? From I, right? So that's what we're checking. So therefore, this thing is from I, right? Because I is an ideal. Maybe I interchanged that again. Maybe that was not a good decision. Sorry. Okay, let's try again. I don't even need this. Yeah, so I need that Z is from I, right? And X from I I orthogonal. So therefore we have B, and let me use invariance right away. So sorry, X, Y, Z. So this one is in I, and this one is from I orthogonal. So this is 0. That's it. Let me now give you an example of invariant form. So example, very important. So if you have a V representation of G, then the form BVXY, which is trace over V, rho V of X, and then rho V of Y. So so V is a representation, therefore you have corresponding homomorphism from G to endomorphisms of V. So you have to take this form, it's bilinear, and it's symmetric, it's additional property that we'll have usually, is invariant. So proof, it's very easy. We just need to check that for any three matrices, X, Y, Z, well, matrices or linear transformations shall form GLV. You have trace of X, Y, Z, right? So here it's a multiplication of matrices. And this is a commutator of matrices. Equals to the trace of X, and then Y, Z. But this is very easy to check. So what do we need? So we just write this down, right? It is X, Y, Z, right? Minus Y, X, Z. Trace, it's linear. So I have, on the left, I have this. Trace of this minus trace of this. It's left-hand side equals to, on the right-hand side, again, so this thing is X, Y, Z minus X, Z, Y, right? And again, trace is linear, so I have trace X, Y, Z minus trace X, Z, Y. So what cancels with what? So this cancels with this, and this cancels with this because trace is cyclic. So I can move Y to the other side. So this cancels with this, and we proved.